Hello, welcome to the presentation on my doctoral thesis. I am Arasan Uthayasuriyan from Midlist Research Lab, and I registered as a doctoral student at the University of Nottingham in the UK as well as at ENTP in France. So before starting my presentation, I would like to thank the European Union which funds my research through the No to Noise project. So in this video, I'll be presenting about the advancements that I made during my PhD, and they are particularly focused on developing advanced vibroacoustic condensed models to predict the acoustic responses of multi-layer structures. Multi-layers are widely used in many industries to have good performances on both structural and noise attenuation sides. If we take aircraft industry, composite structures are used in many aircraft parts to increase the structural performance, but they perform poorly on the vibroacoustic side. Poroelastics have the opposite behavior of having good acoustic performance and poor structural performance. So by combining these two kinds of materials, we form a multi-layer structure from which we could realize good performances on both aspects. So to analyze these multi-layer structures, many types of vibroacoustic models are being used, and one such type is called equivalent or condensed plate models, which is the topic of my doctoral research. So we will see what these equivalent plate models are and why do we use them, what are the basic details that we should know to understand these models, what exactly do we get from these models, and what is the process or methodology that we have to follow to get these outputs. So that's the first part of this presentation, and after that I'll move on to the 4 advancements that I made during the course of my PhD. So first we'll focus on what are these equivalent plate models and why do we use them. So to answer these questions, we could look at 2 important advantages that they provide. So let's look at the first one. We have seen that these multi-layer structures are used to improve the structural and vibroacoustic performance, but when we go for finite element computations of these structures, we will need different mesh size or different mesh types suitable for different materials that we use in the layered structures. Additionally, for an industrial problem like cabin flooring design of an aircraft, if we mesh each and every layer of these structures, it would result in larger number of degrees of freedom, which would require more computational time and power. Alternatively, if we could convert this multi-layer system into a single layer which would exhibit the same or equivalent vibroacoustic response, we will end up with only one layer of material to handle, and this would help us in reducing the total computational time and power for the finite element simulations. Alright, so now let's look at another major advantage of these models. Depending on the types of layers used in the multi-layer structures, these kind of different waves could propagate inside the layer, which would then contribute to the global response of the structure. If the layers are too thin, we could observe that only bending and shear contribute to the global response of the system, and generally these two wave motions are categorized as antisymmetric wave types. On the other hand, if the multi-layer structure is thicker or contains any soft materials inside them, so then along with the bending and shear, the compressional motion also influence the response of the multi-layer structure. So now here the equivalent plate models help us to understand the interaction between the antisymmetric motions such as bending and shear. For example, at a given frequency, how this multi-layer structure is going to behave. Is it going to be controlled by the bending of all the layers or only some layers, or how these different motions affects the damping nature of the structure? What are the interactions between the symmetric and antisymmetric motions, and when are they going to be important? So these kind of understanding we could be obtained. This kind of understanding could be obtained from these equivalent plate models, and this information would be quite useful while designing the multi-layer structures. Okay, so now to understand these models, we need to know a few fundamental information, and those are the propagating waves inside the structure due to the vibration, which we have just seen. For example, if we consider a transmission problem across a wall, the wall would vibrate in this complex manner due to the sound source on the left hand side. If we break down this complex motion, we could find that bending, shear, and compressional waves are fundamental waves that propagate in these structures. There are different equivalent plate models in the literature, but they mainly differ from each other by what are the propagating waves they allow in each layer of the multilayer system. Why are they allowing only few wave types and not all? It is mainly to reduce the complexity level of the theoretical formulation of the model and thereby targeting only specific problems. So, by formulating these equivalent plate models, what do we get as an output? For this, we will look at three models that are widely used in the literature and industries. In the added stiffness model, only bending wave motion is considered in all the layers of the multilayer system. In another popular model called RKU, which was developed for three-layer systems, the outer layers are assumed to be controlled only by bending, and the core layer is controlled only by the shear. The third model, developed by Guyader, both bending and shear waves are allowed in all the layers of the multilayer structures. All these models convert the multilayer structure into a single isotropic thin plate with frequency dependent material properties such as the bending stiffness or the Young's modulus, and these material properties will be given as inputs for the finite element calculations. We should note that these models exhibit only bending and shear effect of the multilayer structures, and mainly neither of these models include compressional motion or the dilatational motion in their formulation. So, knowing these basics of equivalent or condensed plate models, now I move on to the advancements that are done to improve these models. The first one is to find the frequency limits of validity of commonly used plate models for vibroacoustic applications. Two types of plate models are commonly used in vibroacoustic theories, and those of Love-Kirchhoff and Reisner-Medlin theories. Commonly, these are referred as thin and thick plate theories, respectively. So here I have plotted the transmission loss curve for a concrete wall subjected to 60-degree plane wave incidence by assuming the structure to be planar, which has infinite lateral dimensions and with homogeneous and isotropic material properties. I would like to point out that I have kept these assumptions throughout my thesis work. Okay, so we could see that the responses predicted by these plate theories deviate after certain frequencies when compared against the reference solution computed by the elasticity theory or the transfer matrix method. The thin plate theory response deviates from this point as it does not include the shear effect, and the thick plate theory deviates from this frequency as it ignores the dilatational motion. Finding these frequency limits of respective theories would be necessary to safely apply these theories, but on this line, there is no clear-cut analytical expression available in the literature which could help us to know their validity or accuracy limits. So, therefore, as a first advancement, the frequency limits of isotropic single-layer plates is analytically expressed. So, here is the overview of the process that is followed to get those expressions. We know that in thin plate theory, only bending motion is considered, and therefore only bending wave is allowed to propagate inside the structure. On the other hand, the thick plate theory includes the shear motion along with the bending motion. But we should also note that both of these theories do not include the compressional motion. Okay, now if I plot the wave numbers k against the frequency for a plasterboard layer from thin and thick plate theories, we could observe two important information here. Firstly, we see that the low frequency behavior is heavily controlled by the bending, and secondly, the high frequency behavior is controlled by the shear motion. Or in other words, the bending and shear wave numbers are low and high frequency asymptotes of the propagating wave number computed by the thick plate theory. As the shear wave number is comparatively lower than the bending wave number in the low frequency range and increases linearly with the frequency, we could limit the thin plate theory by defining a ratio C between the bending and the shear wave numbers as I have shown here. So this particular definition would help us to find the this analytical expression for the frequency limit of thin plate theory. For the frequency limits of a thick plate theory, we could compare the propagating waves of a thick plate and an elastic solid. Note that the principles of elasticity includes the compressional motion of the structure along with the bending and shear, whereas the plate theories neglects the compressional motion. Using the antisymmetric and symmetric velocity expressions proposed by Deman Long in 1974, we could write the admittances as shown, which correspond to the symmetric and antisymmetric motions of the physically symmetric multilayer. Since a single layer is a structure of a symmetric type, we could use these relations for our present analysis as well. So you may mind that we could only separate the symmetric and antisymmetric behaviors as shown here if the multilayer is physically symmetrical. For asymmetric multilayers, these expressions would be complex, and those are out of the scope of my thesis. Okay, now these expressions could be rewritten in a matrix form like this. I would like to mention that YA could be directly obtained from plate theories, as plate theories capture the antisymmetric motions. To obtain the symmetric admittance YS, we could equate this matrix to the transfer matrix of an elastic solid, which actually comes from the transfer matrix method. And from this equation, we could obtain the symmetric admittance of an elastic layer. Now, since we know the antisymmetric and symmetric admittances, similar to the process that we followed to obtain the frequency limit of thin plate theory, we could also express a condition between the symmetric and antisymmetric admittances as I have shown here, which would help us to get the analytical expression for the frequency limit of thick plate theory. We have to note that many plate theories do not include the compressional motion in their formulation. This means that the frequency limit shown here is not only applicable for Reisner-Mindlin theory, but also for many other plate theories in general. So now if we plot the transmission laws for a concrete layer with the mentioned properties, we could observe the well-predictive nature of the frequency limits computed by the analytical expressions that I have shown before. So to demonstrate the validity of these frequency limits, a dedicated web page has been created in the APMR website. You could find the link for this page on the description of this YouTube video. The web page contains the details that we discussed now. I'll just open the web page. Okay. So for example, if you want to see the effect of the plate thickness on the wave numbers, you could change the values of the thickness here, and you can observe its effect on the dispersion curves on the right hand side here. So if we scroll down further, you could find an interactive application for the frequency limits of plate theories. In this application, the transmission loss values are plotted for different theories for the plate properties shown on the left hand side under 60-degree plane wave incidence. The frequency limits correspond to the thin and thick plate theories are also plotted with the gray and green color dashed lines respectively. So if you want to see the effect of plate properties on these frequency limits, you can just change a property value and see its effect on the plot. For example, here if I change the Young's modulus of the plate to 2 GPa, around 2 or 3 GPa, and for this value you could see the instant predictions of the frequency limits and the variation in TL responses from different theories using this interactive application. Suppose if I change the density to 3000 kg per meter cube, so we can see that the thin plate theory starts to deviate from this frequency, as it does not include the shear motion of the plate, whereas thick plate theory could match up until this frequency from the TMM, as the compressional motion starts to influence the structure's behavior after this frequency, as you can see here, and the plate theories do not capture this compressional effect in their formulation, which is why you are seeing these deviations after these frequency limits. Okay, let me get back to the presentation now. Okay, so the second advancement is regarding the development of a simple equivalent plate model for 3-layer sandwich plates. Among the existing condensed plate models, Guyader and RKU models are widely popular due to their effectiveness to capture the natural response of the multilayer structures into a single layer. But one of the major challenges with regard to these models is the implementation process. as these models require many complex computations. Implementing and testing of these models would take considerable amount of time, and in addition, the Goyather model requires solution tracing techniques to be implemented to find the physically propagating wave of the multilayer structure. So to avoid all these complications, a simple model is developed for three-layer structures from the asymptotic observations made by Boutin and Vivage using their homogenization approach. So to understand the methodology, let's go back a little and see the wave number plot of a single layer again. We could see that at the low frequency, to put it in other words, we could see that the low frequency asymptote of the propagating wave number is the bending wave number, and the high frequency asymptote is of the shear wave number. On the other hand, if we see the nature of the propagating wave number for a three-layer sandwich structure, it seems like an S-shaped curve or sigmoid curve, and the asymptotical behavior looks different than the single layer structure. So now let me go a little deeper here. Instead of the wave number, if I plot the equivalent bending stiffness, we would be able to observe some interesting asymptotical behaviors of the three-layer structure. At low frequency, the structure bends as a whole, and all the three layers contribute to this global bending. At high frequency, the core decouples the skins, and this wave motion is controlled mainly by the individual bending contribution from the skins. Boutin and Vivage call this behavior as inner bending in their homogenization work. At transition frequency, the shear modulus of the core controls the motion of the structure. These are the three important behaviors of a three-layer structure. But to get the values of dEq or the equivalent bending stiffness at all frequencies, we would need a fourth parameter, which is called as the slope at the transition frequency. This parameter is influenced by the ratio between the core and the skin thicknesses, and it can be expressed by a polynomial as a function of this ratio. So now, with only these four characteristic parameters, a full frequency response can be obtained by this relation I have shown here for the computation of equivalent bending stiffness, which is denoted as dEq here. So now let us look at a validation case with a three-layer structure with aluminum skins and a soft core, as I have shown here. At low frequency, an asymptote can be drawn from the bending contribution from all layers. At high frequency, an asymptote can be drawn from the bending contribution only from the skins of the sandwich. And the transition frequency can be computed from the shear modulus of the core layer. So with this information, we could obtain the full frequency range response as I have shown here, which is in high agreement with the Goyather model. So therefore, this new simple model could provide the following advantages over the other existing condensed plate models. Due to its simplicity, this new model will be easier for implementation compared to the other models. Due to the same reason, it can act as a handy tool to optimize the sandwich layers to achieve the desired performance. And finally, it can be helpful to understand the physical behavior of the sandwich structure at different frequency regimes. Now I'm going to show you another web application for the Sigmoid model. So as you can see in this web page, the basic details of the sigmoid model is given with some illustrations, and if you scroll down below, you could find an interactive application. So here I have taken a three-layer structure with the steel skins and a soft core with its properties on the left-hand side. On the right-hand side, the equivalent bending stiffness of this three-layer structure is plotted along with low and high frequency asymptotes. So if I change the Young's modulus of the core, we could see that it affects mainly the position of the transition frequency and not the other characteristics of the bending stiffness profile. But if I change the thickness of the core, we could observe that it affects the lower asymptote as well as the transition frequency. We could also see the effect of these properties on the equivalent loss factor. For example, we could see that as I change the Young's modulus of the core, the frequency position of the frequency position of the peak loss factor changes, and its peak value is heavily controlled by the loss factor of the core, as you can see from changing its value. So we have seen how equivalent plate models behave for sandwich structures, but are these models are these models sufficient enough to completely describe the vibroacoustic behavior of the multilayer structures? We can take an example to answer this question. If a three-layer sandwich structure made of plasterboard skins and the glue as a core, we could note that up until this critical frequency, the transmission loss is well predicted by the equivalent plate models. But if we focus our attention to the high frequencies, we could observe poor correspondence between the equivalent plate models and the response from the elasticity theory. And this is because the existing equivalent plate models do not include the compressional or the dilatational effect of the multilayer structure in their formulation. So this particular point can be supported by performing the Lamb wave analysis as well. In short, Lamb waves are the elastic waves that propagate in the structure, and these waves are considered to be complete as they arise from solving the complex elasticity equations. Here I have presented the zeroth order antisymmetric and symmetric Lamb wave solutions for both stiff and soft core configurations. I would like to stress on the point that the antisymmetric wave correspond to the bending and the shearing motion of the structure, whereas the symmetric wave correspond to the compressional or the dilatational motion. As we could see from this plot, Guyader model predicts the correct antisymmetric wave solution, but unable to predict the wave solution correspond to the symmetric motion. This could particularly lead to erroneous results if the core is too soft, because the compressional mode is also contributes to the complete vibrating motion of the structure after a certain frequency. So therefore, a new condensed model is developed which includes compressional motion along with the bending and shear motions of the multilayer system. Okay, now let's see the methodology of this new condensed model. Including the compressional motion along with the bending and shear would normally be tricky, but in the case of symmetric multilayers, we could inspire the work done by Dim and Long, where they demonstrated that we can decouple the symmetric and antisymmetric motions, and we could express the behavior of these two decoupled plates in a separate manner. Okay, the next question might be, how are we going to do that? For this, we could perform the admittance analysis to get some insights. For example, I have taken a three-layer sandwich structure with a thicker soft core and steel skins. For this configuration, I have plotted the admittance curves at the normal incidence, that is the theta equal to 0, and at an oblique incidence for theta equal to 60 degrees. A few important observations could be made from these plots, which would help us to express the properties of symmetric and antisymmetric condensed plates. First, at both incidences, we could see a peak around 200 Hz, which correspond to the compressional frequency of the structure. Secondly, at 60 degree incidence, we see a peak around 6000 Hz, but we see this peak not only on this antisymmetric admittance, but also on the symmetric admittance. And the position of this peak is controlled by the bending stiffness of the structure. The existing equivalent plate models express the impedance of an equivalent thin plate like this, but note that, as I have mentioned a couple of times before, this kind of definition accounts only for bending and shear of the multilayer structure and not the compressional mode. So in our present case, we have decoupled the single layer condensed plate into two equivalent thin plates, and since both symmetric and antisymmetric admittances have the same peak, which is controlled by the bending stiffness, we could keep this term common for both of these impedances. We also note that for different incidences, this shaded region is identical and it is controlled by the mass term of the impedance. Although the region is identical at different angles, the nature of the symmetric and antisymmetric admittances are in fact different. As you can see, the antisymmetric admittance decreases with the frequency, whereas the symmetric admittance increases and have its peak around 200 Hz and then decreases with the frequency. Therefore, two different mass terms are introduced for each impedance like this, and it may be also noted that at normal incidence, the entire region is actually controlled by the mass, as the contribution of the stiffness is 0 at normal incidence. So in a generic symmetric multilayer system, we could express the impedances of these two decoupled equivalent plates as I have shown here, with the frequency dependent properties dEq, rho a and rho s. Okay, so how do we compute these properties? dEq is usually taken from any existing equivalent plate models or a simple equivalent plate model that we have seen a few minutes before for 3-layer structure. To obtain the frequency dependent properties rho a and rho s, two approaches are proposed. The first one is a more generic way where the impedances are computed at normal incidence using the transfer matrix method, or shortly called as TMM, and then from these impedances rho a and rho s are obtained. So to demonstrate the second approach, a symmetric 3-layer structure is taken where the skins are assumed to act as a mass, and the compressional stiffness of the core is modeled as a spring. For this mass spring mass system, we assume rho a to be the equivalent or the average density of the structure, and rho s is expressed as shown, which has the effect of the symmetric motion or compressional motion of the 3-layer structure through the spring stiffness k. Even though I show this approach for the 3-layer system here, it can be extended to any number of layers in fact. We should also note, or we should also keep in mind, that these three dynamic properties do not depend on the angle of incidence, and therefore they can be called as the intrinsic properties of the characteristic properties of the multilayer structure. Therefore, in summary, the existing equivalent plate models require only one dynamic property, which is dEq, while the newly developed condensed model requires three dynamic properties dEq, rho a and rho s, to capture both antisymmetric and compressional motion of the multilayer structure. You may note that we could find the equivalent Young's modulus Eq from the equivalent bending stiffness that is denoted as dEq. This equivalent Young's modulus would go as an input in the finite element calculations to compute other vibroacoustic quantities. So to show the validity of this model, a sandwich structure with steel skins and soft core is taken and subjected to diffuse field excitation. Here I have chosen diffuse field to demonstrate that the intrinsic nature of the condensed properties dEq, rho a and rho s. So as a reference, a transmission loss computed from the full elasticity solution or the transfer matrix method is shown here. Note that we could observe two sudden drops in TLs, the transmission loss from this curve, and these are from the resonance due to the compressional and critical frequency effects respectively. Now, if we plot the antisymmetric contribution from any existing equivalent plate model, we get response like this, and we could clearly see the deviated or erroneous response from this model after 100 Hz. Though the current equivalent plate model predicts the correct critical frequency compared to the elasticity theory, it underestimates the TL response of the multilayer structure at this frequency. And further, we could clearly see that the current equivalent plate model missed to predict the compressional frequency effect in the TL, as it does not contain compressional motion in its formulation. Now, if we plot the response from the newly developed condensed model, we could see that it correctly captures the vibroacoustic performance throughout the frequency range by including both symmetric and antisymmetric motions of the structure. Okay, now I'll show the validity of the new condensed model using the web application. So you can see the interactive application for this part on the same condensed model web page itself by clicking the TL option here. Yes, so for this 3-layer structure, the transmission loss values are plotted from the sigmoid model and the transfer matrix method. Here we clearly see that the equivalent plate model, which captures only antisymmetric motions, deviates from the TMM after 100 Hz or around this frequency, as it does not capture the effect of compressional motion of the structure. But if I show the condensed model now, but you can see that the new condensed model captured this motion very well and thereby having good correspondence with the reference solution obtained from the TMM. You could note that the core is too soft compared to the steel skins, which easily allows the compressional motion at low frequency. As I increase this Young's modulus of the core, it slowly becomes stiff for the compressional effect, and therefore both the new condensed model and the TMM match with the equivalent plate model, right? So this means that only antisymmetric motions such as the bending and shear influence the structure behavior for these kind of multilayer properties. As we reduce the Young's modulus of the core, we could see the evolution of the compressional motion's influence in the TL computation, which is very well captured by the new condensed model. Okay, let me get back to the presentation. Okay, now it's time to implement this newly developed condensed model into the finite element formulation to realize the benefits on the total computational time. We know that for a multilayer like this, we need to keep only the condensed layer with the dynamic properties EEC, rho A and rho S. In our FE implementation, we modeled this condensed layer with thick plate elements instead of thin plate elements. Now, you could ask, how can you model with the thick plate elements while the condensed models are based on thin plate theory? Because if you remember, we used the thin plate impedances to get the dynamic properties of the condensed layer. Then why did we go with the thick plate elements instead of thin plate? The main challenge with the thin plate elements are they require special shape functions which should offer the non-zero higher order derivatives. This particularly leads to complex implementation process, and additionally, if you want to run the simulation, for example with the higher order elements, we need another set of special shape functions which are even more complex. So therefore, to avoid this, we model the condensed layer with the thick plate elements, which has two different parts in the stiffness matrix definition. We have a bending part KB and a shear part KS, and these element stiffness matrices can be easily obtained by the standard isoparametric shape functions. For a conventional plate, bending and shear information would be described by the Young's modulus and shear modulus respectively. But in the case of condensed or equivalent plate, we know that both bending and shear information are condensed into the equivalent Young's modulus. This means that we cannot account for the shear again through the KS matrix, and we need to somehow remove the influence of it. So we cannot simply make the shear stiffness 0, as we need both KB and KS as non-zero matrices to be able to solve the problem with the thick plate elements. But if we introduce a penalty factor, a gamma on the shear part, we could observe an interesting point. If I increase the value of the penalty factor, we could observe that the thick plate response is actually very much closer to the thin plate response. We could exploit this interesting behavior of the thick plate elements to retrieve the behaviors of the thin plate elements without going through all the hassles of implementing special shape functions. So with this observation, we are now confident to use the thick plate elements with the penalty factor on the shear part to model the condensed layer. Now let me quickly revise the standard finite element equation formulation to solve the vibroacoustic problem with the elastic solid layers. The solid layer would be described by the displacement variable W to satisfy the dynamic equilibrium equation. The surrounding fluid layer would be described by the pressure variable P to satisfy the Helmholtz equation. Then the fluid and the solid layer would be coupled using the Euler's equation. Following this scheme, we could form a standard finite element equation to solve the vibroacoustic problem. Note that as I would be solving the problem to compute the transmission loss with imposed pressure field on the left hand side, there is no loading condition given on the FE equation. Now I'll switch from 3D to 2D view for the sake of simplicity. Okay, so I think it's much more clearer now. Okay, now I'll talk about how the new condensed model is implemented into this framework. If you remember, we have decoupled the condensed layer into the two layers corresponding to antisymmetric and symmetric motions. Therefore, in the finite element setup also, we have two plates. One is described with antisymmetric displacement WA, and another plate is described with the symmetric displacement WS. So now to solve this system, we have to couple these two plates. For achieving this, we are going to refer the work done by Dim and Long again. So let me go back to the place where I introduced the Dim and Lang work to get the frequency limits of plate theories. Using these antisymmetric and symmetric velocity definitions as functions of velocities at the emission and the reception side, we would be able to couple the antisymmetric and symmetric plates. And for this purpose, the pressure degrees of freedom at points O and N are split for convenience. As we have seen before, the plate displacements, that is WA and WS, are coupled with the fluid layers pressure degrees of freedom PO and PN using the Euler's equation. So now this scheme is translated into this FE equation, where the dynamic equilibrium equation of antisymmetric plate is written with the Ka and Ma with the equivalent properties Ek and rho A. In the next row, the dynamic equilibrium of a symmetric plate is written with the Ks and Ms with the equivalent properties Ek and rho S. Then the displacements WA and WS are coupled with the pressure degrees of freedom PO through the coupling matrix C, using the relations between WA and WS as functions of displacements at point O and N. Similarly, the pressure degrees of freedom at point N is coupled with the displacements WA and WS in the same manner as before, using the coupling matrix C. So to compare the finite element results with the TMM, the structure is assumed to be of infinitely extent along the lateral directions. This could be achieved by applying periodic boundary conditions on the lateral edges of the domain. So to compute the transmission loss, the ratio between the incident and transmitted power needs to be calculated. Once we solve the system, the surface impedance of the condensed layer can be calculated, from which the reflection coefficient can be obtained. The incident pressure is then could be computed with the reflection coefficient, and from this from the incident pressure, we would be able to calculate the incident power. As we could get the pressure and velocity profiles at the reception side after solving the finite element equation, of course, the transmitted power would be calculated with these profiles. Now we will look at two validation cases of this finite element approach with the condensed layer. In the first configuration, the multilayer is soft core bonded with the two plasterboard skins. If we compare the responses of different FE approaches, we see that the proposed finite element approach matches well with the conventional 3D finite element. If we focus our attention on the computational time, we see that the proposed condensed finite element approach runs 50 times faster than the conventional 3D finite element. Let's see the second configuration now, where a double wall partition case is taken. In this typical double wall construction, a glass wool porous layer would be decoupled from the plasterboard skins with some air gap, typically around 1.5 millimeter. For this configuration as well, we could see that the proposed FE approach exhibit good correspondence compared to the reference solutions. On the computational time, we see that the condensed FE scheme takes 550 times lesser computational time than the conventional 3D finite element, which is a significant benefit that we could get from the condensed models. Alright, so now I have reached the end of this presentation. So in summary, there are 4 advancements that I had done during my PhD. At first, the frequency or validity limits of commonly used plate theories are obtained. Those are clear-cut analytical expressions which depend on the geometric and mechanical properties of the single layer structure. These expressions would be quite useful to many vibroacoustic models, including the equivalent plate models, but they are not applicable to layer with the dynamic properties at the moment. Secondly, a new simple equivalent plate model is developed for 3-layer structure using the observations made from the homogenization approach by Bhutan and Vivek. The model is simpler than the other equivalent plate models, and therefore we could benefit from the quicker implementation time. Also, this model would be a handy tool to understand the physical behavior of the sandwich structures. On the downside, it covers only thin 3-layer structure with a soft core. Although the equivalent plate models are efficient to reduce the computational time and helpful to understand the physical behavior of the layered structures, they are mainly restricted to only thin structures. Therefore, a new condensed model is developed which extends its applicability to wide range of thin and thick multilayers, and it can also be applied to multilayer sound packages with poroelastic layers. But it requires the structure to be physically symmetric. And finally, the new condensed model is implemented into the finite element framework to realize the benefits the new condensed model provide to the users. As the condensed model is limited to only symmetric structures at the moment, the finite element approach also limited to the symmetric structures. Coming to the perspectives side of the work, we could perform a similar admittance analysis for the condensed plates to find its validity limits as we did for the layer with the static mechanical properties. Since the condensed model condensed finite element scheme is tried only with the airborne excitation, we could include other excitations to improve the finite element package. Another perspective could be extending the condensed model for asymmetric structures by correctly modeling the coupling conditions between the antisymmetric and symmetric admittances. Even though the condensed model is applicable to planar structures, we could try to use the condensed model properties in the curved structures to study its validity on these kind of curved structures. Other interesting aspect or perspective could be modeling the imperfections on the bonding between the layers, and on this front currently Nicola Okie from LVA is doing his PhD on this topic. Out of the 4 presented work, 3 work have been already published, and the one on the finite element implementation is currently with the Journal of Sound and Vibration. So that's all I would like to share with this video. So I must say that it is a pleasure presenting my work, and I thank you very much for your attention.